Okay, so hello everyone. I hope you can all hear me. So far we have been discussing some very basic properties of fluids and plasmas, and now uh, going to look at how we can use these equations to understand a bit about uh, the origin of magnetic fields in the universe. As I've argued before, uh, that pretty much every system and over any scale that you observe shows a magnetic field. In slight discussion of turbulence, I also argued that the dissipation, not by the molecular properties of the medium, such as viscosity or the resistivity as in this equation, but through the turbulent diffusion that might originate, as I will show in a bit, from this type of equation, from this type of term, that leads to a very faster decay of the quantity of interest, be it velocity field or the magnetic field, that it is expected to decay, and therefore there is a need to build it again. There is need to continuously generate the magnetic field or the motion against that can sustain itself against the turbulent dissipation, and that will be the main theme of today's thing. I want to actually finish rather quickly today so that we can have some live question answer session today. That is my plan. So what I suggest is that and also someone, I think John was asking if these slides can be uploaded. So if you have access to the PB works, I just uploaded this updated lecture notes this morning. So you can all have a look at these slides from the PB Works website. And I do hope that you all can log in from that and make use of these. These will be under section, I think, under folder lecture notes. I think it will be mentioned there. Just says fluids and plasmas.pdf kind of thing. Okay. So yeah, so starting from the Maxwell's equation, making approximations such as non-relativistic limit and stuff, and we have now arrived at an equation which governs the evolution of magnetic field in any system where there is a motion. V is a motion in the plasma. So as you can imagine, that this could drive as a source term to produce a magnetic field. After all, it can grow or decay. This is always a dissipative like term, as you know from your heat diffusion equation. If I didn't have this term, suppose the velocity is 0, you only have a del B by del T equal eta, which is a positive quantity. It's a microscopic resistivity of the medium, Laplacian. So that's a heat diffusion equation, which you all might have seen before. If not, then just try to take a Fourier transform and you will write an equation which is del B by del T equal in a Fourier space minus eta k square B. And the solution is exactly like exponential minus eta k square T. That is how it will write. So it will decay exponentially in time through this term. But that decay may be very, very small or very slow. As I argued that this eta is very, very tiny in the astrophysical cases, 10 to minus 4 seconds it will take for any charge imbalance to decay away, thus shorting out the electric field, but not the magnetic field. Okay. And this equation, you will keep hearing if you are interested in the magnetic field, regardless of the system you are interested in, accretion disk, black holes, accretion disk around black holes, say, or neutron stars, sun, stars, any system, so long as you are interested now in the magnetic field, you will keep hearing about this equation, induction equation. Okay, I'll comment a little bit more on this later. And if I do exceed a little bit time today, I hope that is okay, because I do want to finish as well as want to interact with you a little bit. So let's just take a small application of this. I have already shown you this equation in terms of the vorticity equation. So please recall your our discussion on the vorticity, del omega by del t was exactly curl of V cross omega, where omega was curl of V. So while you note the similarity, please also note the differences, that here B is not curl of V, whereas omega was curl of V. So that was highly, highly nonlinear. This is at face a linear equation in B. And every term contains B, so therefore it makes it very interesting that B equals 0 is a full solution of this equation. And therefore you must always require some amount of seed magnetic field in order to evolve the magnetic field using this equation. Okay, that's a magnetogenesis problem. And if you are further interested, just look up something like Biermann battery mechanism and magnetic fields in the early universe. Okay. But for most systems of our interest, like say the stars, sun, galaxies, these are born with tiny bit of magnetic field because the interstellar medium or the medium that is forming these objects already comes with some magnetic field. In an ideal case, when there is no resistance, like eta is 0 and nu was 0 for the vorticity, we saw that the circulation was a conserved quantity. So we can similarly think of, and I had already told you, this Kelvin circulation theorem has a magnetic counterpart in magnetic flux freezing, which is also known as Alfvén's theorem. Okay. So now, for a moment, just think of ideal MHD. That means eta equal to 0. By recalling the discussion on Kelvin circulation theorem, you can immediately write that the total time derivative, the Lagrangian derivative, over surface S of B dot ds, the flux of magnetic field through a surface S, through a bounded surface S, is 0. This we have rigorously seen before, and I'm just rewriting the same equation. The derivation will follow exactly like for the case of vorticity. Just like the flux of vorticity through a surface was 0 there, which we defined as circulation. Here you just call the B dot ds is also 0, the derivative of that. So that means the flux must be conserved quantity. B dot ds must be conserved. As an illustrative example, take say star like the sun. Suppose this is a star like the sun, and say a very typical diffuse field strength of the star is 1 Gauss, and its radius is 10 to the 6 kilometer. Right? So it's like 1000 megameter is supposed the radius. It's very close to the solar case, or maybe a little bit bigger than sun, but still, you have a 1 Gauss field strength and 10 to the 6 kilometer of star, which undergoes a collapse. As it collapses, it will of course lose mass, and because you know that the magnetic flux is frozen to the plasma, if there is suppose a stellar wind or solar wind that we know, the magnetic flux is frozen to the plasma. So even tiny plasma element that is moving out in space will also carry the magnetic field with it, because the magnetic field is pretty much frozen with that plasma. So if I throw away matter with this, and there is a mass loss, that mass loss will also be accompanied by a magnetic field loss. Anyway, you can define a total flux of magnetic field from a surface like this, right? So you can take a B1 and multiply that by the entire surface of the star, which is 4 pi r square, and that flux must be a conserved quantity, right? So as if you say that there is no mass loss, and you simply imagine a collapse of a sun-like object to say a white dwarf-like object, which will go from 10 to the 6 kilometer to say 10 kilometer, or say a neutron star, more like a neutron star object. A neutron star has a radius of 10 kilometer roughly, right? So you can work out what should be the strength of the magnetic field, right? Strength of the magnetic field. See, you have already encountered a very powerful theorem before, which was if you stretch a vortex tube, we found that the local vorticity omega was proportional to the L. So the strength of the magnetic field, that is not conserved. It's the flux through the surface that is conserved. That leads to the strength of magnetic field in the neutron star case which is B1 times R1 by R2 square. So this, it goes as the square factor with a ratio of the radius between the two cases, right? So you can write B2, 4 pi will cancel. So B2 R2 square is equal to B1 R1 square, gives you a rough estimate of magnetic field, which is 10 to the 10 Gauss. These are the strongest magnetic field, examples of strongest magnetic fields that we know in the universe, right? Roughly. Neutron stars or the magnetars can have magnetic fields exceeding 10 to the 14, 10 to the 15 Gauss. So it remains to be understood what is the origin of that extra order of magnitude. And it's not easy thing to explain, by the way. This is a simple application of magnetic flux freezing. You take a star, you take a body, let it collapse to form another body. Simply by the factor by which it collapses, take the square of that, multiply to the original magnetic field. This gives you a rough estimate of the magnetic field in this body now. It's a very, very strong one. So you see that simply by collapsing or expanding the bodies, you are changing the strength of the magnetic field. Right? But technically speaking, this is not known as, or this is not called as the generation of magnetic field. The magnetic field was not generated in this case. It is the same magnetic field which you have simply collapsed or expanded. So when you call the generation of magnetic field, what do you call a generation of magnetic field is possible only through the velocity. That means velocity in the plasma will come with its kinetic energy. And if you can convert part of that kinetic energy into the magnetic energy, that process is known as a dynamo process. Now, dynamo, just like your usual dynamo that you might have seen, here it's a self-sustaining dynamo. It's a motion in the plasma, generates and drives the magnetic field in the same plasma. Okay. It's unlike the situation when I can have a current carrying wire somewhere out in space, and here in the center, which is say a different body, I can have a magnetic field through the current at infinity, suppose. That is not what is dynamo. That's and that is not what you consider as a self-sustaining dynamo or magnetic field. So the dynamo is a process in which you convert the kinetic energy to the magnetic energy, but that has not happened in this case. Right? Simply a pure collapse and pure application of flux freezing. But if by some mechanism, if the flux changes, even the flux changes or increases through an area element, if the flux increases, that you would call somehow a generation of magnetic field. That's what is leading to larger flux through the surface, and that would be defined as the dynamo process. Increase of magnetic field is thus possible just by the application of flux freezing, but this we normally would exclude from the definition of dynamo. But as you see that it is very easy by a collapse to increase the magnetic field. Okay. And if somebody asks you what can be the possible sources of very strong magnetic fields in, say, the neutron stars or the white dwarfs, you take the factor for the white dwarfs, you will get some very rough estimate of white dwarf. White dwarfs have a magnetic field on the order of, say, 10 to the 5, 10 to the 6 Gauss. And if you work out the radius factor between the white dwarf and the star, like sun will collapse to become a white dwarf, right? So if you take that kind of an example, just replace R1, R2 by those, come up with a number, you will see, or maybe even surprised, that the strengths of the white dwarfs can be very easily explained by simple flux freezing type argument. Okay. So these may be one source of strong magnetic fields in the compact object. So compact objects typically have a strong magnetic field simply by the same reason, right? Because every body that is there in, say, the galaxy, it is to some extent magnetized always. Okay, so let us just recollect all our thoughts on this topic, which is Maxwell's equation, the MHD, in some sense, what you call magnetohydrodynamics. It's a non-relativistic limit of Maxwell's equation, where we model the plasma as a single fluid, where you don't anymore talk about electrons and ions separately, but you think of a single soup of medium which is charge neutral. Yeah? So the plasma element, we have spent a lot of time in defining the fluid element and a plasma element. What is the defining characteristic of those? Under what conditions you can define those? That we have gone through in detail. Without collision, for example, it is not possible. Mean free path defines the collision, and mean free path must be very small than the fluid element, size of the fluid element. That means the collisions become the defining property of your plasma and fluid description. And that it is very highly conducting. Right? So while a small segment of plasma can be charge neutral, given the charges are free to move, they can move plus and minus in opposite direction while maintaining the charge neutrality, but they can still drive current. So current you can write, as you know, is Q charge density rho times V, electron and proton, suppose they are there. So you can work out what is the charge density, what is the current density. Typical Lorentz force, as you know that if there are electric and magnetic fields, they will exert the Lorentz force on the plasma, right? So there are two types of things. One is the Lorentz force, one is the motion is pushing the magnetic fields around, as we saw here, right? Motion is pushing the magnetic fields around, but there is an additional effect that these magnetic fields will push back on the flow. It's just like Newton's third law, right? Every action has a reaction. So Lorentz force is that reaction, that electromagnetic fields will exert this force on the fluid. So they will modify that. But that is called a non-linear limit. In a very kinematic description, you can imagine that the motion is given and the magnetic fields or the electromagnetic fields are so weak that you only want to understand how does that flow field lead to the generation of magnetic field. That's a kinematic approach. And you will also find that the electric part of the force is neglected in the MHD because it's very, very tiny. If you work out the ratio between these, rho E times E, that is the electric force, divided by, say, this magnetic force, you will find that this is of order V square by C square. Okay? So I will not go, I'm not going into too much detail, but in MHD, typically you keep, it's a very funny non-relativistic limit where you keep the terms of order V by C and you neglect only terms of order V square by C square or higher order. And if you take the ratio between this term and that term, you'll find that this is of order V square by C square, the non-relativistic limit of MHD. You will throw away the electric part because it's very, very tiny compared to the magnetic J cross B. So clearly, if you now go back to your Navier-Stokes equation, Navier-Stokes equation can have what? That's a total, we derived this, right? Del V by, without this term, we have already seen this in terms of Navier-Stokes equation. And you can always add forces. After all, this is just a Newton's law of motion. All the forces you add on the right hand side. Now there is in the MHD additional force, which is J cross B by C. So if you work out per unit mass, that's the force that you'll find. It's a Lorentz force. Yeah. And when you work out per unit mass, you'll find that this is J cross B by rho. So that type of term you get. Okay. So that is for the momentum balance. So in the MHD, your Navier-Stokes equation modifies to include also the magnetic contribution on the right hand side. It's very, very non-linear. As you can see, this is V dot V is also like a non-linear term. Here J cross B, J is curl of B. So curl of B cross B, which is also non-linear force. Okay. So this is only for completeness. Most people nowadays are solving all of this on computers. And it's useful to still remember how you arrive at these equations and what are you solving in those boxes. That is good to remember all the time. Okay, so in MHD, you ignore the electric part of the Lorentz force. We also have seen that eta going to 0 in the induction equation. Induction equation, please remember, you should always remember the induction equation like this, say, or better form is this, when eta is non-uniform. When eta is 0, it's an ideal limit. And that leads to the flux freezing, that the magnetic field is frozen to the plasma. So wherever you take the plasma, it will carry the magnetic field with it. That's the statement. That's why it's called freezing. flux freezing. So flux is frozen to the plasma in the limit of eta going to 0, which is the ideal MHD. You sometimes also call it ideal MHD. If the velocity is 0 in induction equation, the magnetic field will simply decay due to diffusion, ohmic diffusion, yeah, or microscopic diffusion. V is equal to 0 in induction equation leads to only decaying solutions. Magnetic field should decay. Please note that B equals 0 is a valid solution of the induction equation. Therefore, you must always require a seed field. Some amount of magnetic field is needed for that equation to drive the magnetic field to its growth, given the conditions are suitable. Formally, you can define the dynamo action, because you want to understand the origin of magnetic field. That means you must know how to generate those. There is hardly any debate anymore that the source of magnetic field in various cosmic bodies is the dynamo action. It's regardless of the system. Of course, the system might be born with certain magnetic field, but that will not be able to explain the various observed properties of the magnetic fields in the system. So I will simply quote a reference which you can read for more information. Formally, the dynamo action is defined as conversion of kinetic energy into magnetic energy. Simply put like this, without any electric current at infinity. So if you are trying to understand the solar dynamo, the dynamo that gives the magnetic field in the sun, you're not supposed to have a current in the galaxy somewhere and seek that as an origin of some magnetic field at the center of that current carrying loop, which may be the sun. So that is not allowed for dynamo. So somehow through the motions, like sun has convection, many stars have convection as their source of motional energy or the kinetic energy. So somehow you can also put it that how does convection lead towards the growth of magnetic energy in those systems? What acts is that flow with the velocity v, which we don't know. You have to solve for that velocity v, which is the most challenging thing, of course, and you will hear more about this from Dhruva later today on the properties of the flow and how difficult it is, or how to think about this nonlinear equation, which has been understood as the most difficult problem. So the flow, this may act as a dynamo in a system. So it's a self-sustaining mechanism. There is always a dissipation, but you have to be able to generate some magnetic field through the flow so that they are in a balance. So the growth and decay are in some sort of balance, giving you magnetic field at any time. That is the source of magnetic fields that you see today in the galaxies. So I've shown in somewhat different way these pictures, but if you look at now the galaxy, so massive objects, right? Entire spiral galaxies like 20 kiloparsec diameter, say 20 kiloparsec. It's a very, very large scale. And if you draw these contours, these are the synchrotron radiation from the galaxies. Based on that, one makes these maps. So you can look up these papers, many papers by Rainer Beck, Andrew Fletcher, and excellent reviews by Anwar Shukuro. So you can read some of these references if you are interested in magnetic fields, the contours, and you can think about why there is no arrow on these lines. Why there is no arrow, but I leave it for you to think. One can do modeling and find out finally also the arrows. So the entire galaxy has a coherent large-scale magnetic fields giving you such coherent large-scale synchrotron radiation. Right? There are these highly relativistic electrons which are trapped in these large-scale magnetic fields giving you synchrotron radiation from this entire galaxy. So if you observe them in radio, you find that the whole galaxy seems to show large magnetic features. Question is, the flow is occurring at such small, tiny scales. Largest scales of the flow can be the supernovae in the galaxies. So say hundreds of parsec. But the galaxy is still many orders of magnitude larger than even the hundreds of parsec. I hope you can already appreciate these numbers of how much is a parsec and light year and stuff like that you might have seen in the other courses. So it's still a very large scale, but nevertheless, given the scale of the magnetic field, there is no motion at those scales. Motion is always occurring at a very small length scale. So the important question here is, okay, I can drive perhaps the magnetic field through the velocity field, but how do I explain the scale of the magnetic field? After all, this may induce the magnetic field at its own scale of the velocity field. Suppose I'm driving something at this scale, it will lead to something at this scale alone. So what is happening that the magnetic field is observed at a scale which is much larger than the driving scale or the scale of turbulence, outer scale of turbulence. So this is known as a problem of large scale dynamo. Okay. That means the growth of magnetic field at very large length scales, larger compared to the scale of turbulence. So how do you cascade the energy, inverse cascade from small to large length scales, this magnetic energy? So that is one thing to understand. Given these observations, these questions were asked decades ago, and people have still been working on these. These are still open field, and people are trying to understand the origin of large-scale magnetic fields. Even if you go to the cosmic web and measure the magnetic fields in the voids on a megaparsec scale, people still find coherent magnetic fields on a megaparsec scale when there is no clear source of turbulence within those voids. Okay. So it's a mystery, the origin of magnetic fields, and it's a very interesting problem. So, and the equation to look at is what we have now derived. Whole MHD equations have been displayed to you before. Let us look at very briefly how do we, in theory, try to understand the mean field or the large scale generation of large scale magnetic field. Large scale dynamo means generation of large scale magnetic fields. That is the large scale dynamo. So if I have a total magnetic field, suppose denoted by B prime, I can split that into two components, which is mean. Mean can have variation over slower time scales and can vary over larger length scales. Okay, so that's a large scale component and a small scale component. Total field can always be written as a large scale component and a small scale component. Okay, B plus B. Similarly, for the velocity field, total is mean plus fluctuation. So this is how one tries to understand or builds model of the large scale dynamo. So I'm just giving you a glimpse of what one does really. The only equation that you have for MHD, suppose in the kinematic approach in which the velocity field is given, you are not evolving, say, the velocity field. Suppose the magnetic field was very tiny to have any impact on the flow. Lorentz force was very, very weak. So that means in the very early kinematic stage, only the flow is playing a major role to drive the magnetic field. So suppose that is the situation and you want to understand how come this very small scale velocity field drive a very large scale magnetic field. That is the question you ask. Okay. So suppose I take this total field in and split that into mean plus fluctuation. Similarly for that property, or this is called the rules of Reynolds averaging, which you will keep hearing eventually if you are interested in turbulence, that the averaging the total will give you only the mean, and Reynolds average of a fluctuation is identically 0. So vector 0. So vector field, bold is vector field. So vector B is vector 0 in all directions. Taking the average twice, double average, gives you the same field, same mean field. Okay, it's not in general true, by the way. So you can think about it. You take 2 times filtering. If you are using some sort of filtering approach, you can find that doing successive averages does not necessarily give you the same quantity, but it's an assumption in the Reynolds average that taking 2 time average gives you the same quantity. I have not yet defined this angle bracket. What is this angle bracket? So Reynolds average you can think of as an ensemble average. What is an ensemble average? So please recall your StatMech courses to understand more about the ensemble average, which is if I have a quantity to average, in this case say the magnetic field, and I have a random variable, in this case, say the velocity field. Suppose there is no mean flow in the problem. Suppose there is no mean flow, so I forget about it. V prime is V. So I can think of various copies of that random variable, various copies, infinite number of copies of this various field, in which it will look slightly different in each copy. Right? It's a random variable. I take one snapshot of the velocity. It looks some random variable, random field in the space. Another snapshot will have another copy of the same random variable, but it will look slightly different with the same statistical properties. That means its moments will all be the same, but it's a different realization of the same quantity small v. Okay. So what we are doing here is that we are constructing an ensemble based on the velocity field, where different members of the ensemble are different realizations of this velocity field. And then constructing that angle bracket, which is an ensemble average, that is constructed based on the velocity field, which was the fluctuating component or the random component. Source of that you can think of in sun, say the convection. In galaxy, this can be deriving from the supernovae, which do not have any systematic. They are the random forcing occurring at random times, random intervals. So they are the origin of these random motions in the galaxy, say. Given I've shown you a picture of a galaxy, let's think of galaxy. It doesn't matter actually, many sources. But supernovae in these galaxies, in these spiral arms, they are the main sources of these fluctuating velocity field. And the question is, from these tiny fluctuations, how do you build a large scale magnetic field that are over scales that are much larger than this supernovae scale? Okay, so that's the question. So I construct an ensemble from this various realizations velocity field and take the ensemble average, and that's the ensemble average applied all throughout for all the equations. Okay, taking double average gives you the same quantity. These are the Reynolds rules. Yeah, when you're lost, just look up Reynolds averaging and Reynolds rules. Take the sum, then you should obey like that. If there is a already taken mean and a product between the two mean, see that one ensemble average here in blue and blue here, B1 and B2, and you take the full ensemble average of that, the mean will be pulled out of the average. Okay, so B1, B2 remains the same. Okay, so the prime is total, unprime is mean. If I have a correlation between the b and small v, which is a fluctuating quantity, that average is 0. Okay, why? Because this is already once averaged quantity. So this can be taken out of the ensemble average, and average of the fluctuation is 0 by this rule here. Okay? And therefore this product is 0. But if I had both fluctuations like small v and small b average, that fluctuation, that is not 0 necessarily. And that is in fact the main source of magnetic field. So I'll come to that. And if I, and they commute essentially with the derivatives. So Reynolds averaging, they commute with the derivatives. Okay, so you could write like that and this like that. So the question is, or the goal is right now that we apply these averaging techniques to the induction equation and write two equations. One for the mean field, and another for the fluctuating field. Okay, so let us do that. So we know that the induction equation has a term which is, now we put the prime here because that is the total field we have now before splitting. And you remember that induction term, right? Del B by del T was curl of V cross B. So you just write V cross B and make the split, which is V plus V, B plus B, and forget about capital V for now. Okay, even here, just ignore this to 0. Even here, everywhere. Say there is no mean flow. We are only interested to see large scale evolution from a small scale motion. So this is the term in green. That's the most important term. The even for the once averaged mean field equation, which is a large scale magnetic field equation. Now your induction equation after averaging looks like this. Curl of this called mean EMF, which is electromotive force, and this is a dissipative term. Okay. If there was no capital V, you can see very clearly that by having correlations between fluctuating quantities, which is small v, average of which is 0, and small b, average of which is also 0, but they can have a correlation, which is V cross B, which does not vanish in general. And that is the main source of the field, of the magnetic field at the large length scale, whose ensemble average is non-zero, right? So the question is, you can already see that just by having a small scale correlations, small scale quantities that are correlated over large length scales, we can actually think of building a magnetic field over much larger length scales with very different coherent properties, entirely from the small scale quantity. So that gives you one handle from the mean field approach to understand that though this supernovae may be very tiny, and thus the magnetic fields that they are driving are also very tiny, they can have a very large scale correlations, and that can actually drive the large scale dynamo. So it's very, very interesting that the source of this large scale magnetic field is actually in the small scales. Okay, this quantity is the mean EMF, curl of mean EMF. But what is the problem right now? As you see, you will keep hearing in turbulence there is a problem of closure. You want to know the evolution of capital B, for which you have to know the source, which is EMF, which is small v cross B. Even if suppose small v is given to you, you still need to know the small b so that you can determine this EMF in order to drive this equation. How do you determine the small b? So you go back here. We know the total evolution equation, which is the induction equation, and we want to know the equation for small b. Small b, you can write b prime minus capital B. Subtract this large scale equation from the total induction equation to write down the evolution equation for the fluctuating field, right? And you get this very horrible looking equation. Why horrible? Because what you get here as a surprise is a term which is V cross B minus E again. So this E, which you want to determine for this equation, contains this small b here. But when you write down the equation for B, that contains E here again. So it's a closure problem. Yeah? So you cannot, to know E, we need to know B, but to know B, we need to know E also. Right? So it's a closure problem. Okay? So it's a very, very painful term, and most people will just simply ignore this term because they just cannot handle this. With this equation, with this term on the right hand side, you cannot really immediately solve this. Okay? You have to close the equation such that this term disappears somehow, because with this you cannot really do anything. Okay. So it's a problem. It's a very typical problem in turbulence. Why this is very hard? We have been saying that the induction equation is linear, but as you can see that this is actually not really the case. This is quadratic in fluctuation, which is non-linear in fluctuation. B cross B, these are both fluctuating quantities. This is still linear in capital B, that is true. But there is a non-linearity coming through the fluctuation. So whenever you have a product, it is still quite a difficult thing to manage and handle. Okay. So the last term is non-linear in fluctuations here. And here. So in that sense, while people might say that the induction equation is linear in B, these are actually not really the case. This is non-linear in fluctuations, and this is just as difficult as the usual turbulence, or at least that much. Okay. So then one makes certain approximations. One very famous approximation is known as first order smoothing approximation, which is known as FOSSA, for which you need to have a closure. So let us just write some closure model, and I am not going much into detail. You can see that this is a dissipative term. Eta is very small for astrophysics, so forget about that, ignore that. Ignore capital V, so only you are left with curl of V cross capital B, right? What does it mean? It simply means that if I have a large scale magnetic field, if I apply some small scale motion, there will be a noise in magnetic field produced by simply tangling the large scale magnetic field. This is a large scale magnetic field. Okay. So for the fluctuation, magnetic field can be the source, can be one of the source. There is another thing known as a small scale dynamo, just like a large scale dynamo, but right now we are talking mostly on the large scale dynamo. Okay, fine. So then you can think of that this quantity E can actually be expanded. So right now you can see that E is equal to V cross B. For B, if you roughly think of integral over a time of a small v cross capital B, that type of term. So what you'll get for E is time integral of V cross V, and capital B will go out of the ensemble average, right? Because this is already an average quantity. So you can see that this is something like a VV correlator giving you the EMF, and can be somewhat Taylor expanded in the capital B. This is what is done here. Just think of this EMF as Taylor expanded into the derivatives of mean magnetic field. And these coefficients here are the main quantities, which are also known as transport coefficient, turbulent transport coefficients. Okay, turbulent transport coefficients. So EMF can be written as alpha B minus eta T curl B. Remember that there is already a term like curl B here, and eta T also comes with a curl B here. So the equation, one of the term you immediately identify as eta plus eta T curl B here, or eta plus eta T Laplacian of B as a diffusion term. I was mentioning, right, that the turbulent diffusion is typically very large, leading to faster decay of turbulence and magnetic fields. This is seen by this kind of term here. Alpha, on the other hand, which is linear with B, or which is proportional, alpha term, the parallel component of EMF, parallel to the magnetic field, that's a proportionality constant alpha. That is actually quite an interesting term, which can lead to the generation of magnetic field. This is still a decaying term, but you want to generate the magnetic field from small scale quantities. And as I've shown schematically here, that the transport coefficient will always be 2-point velocity-velocity correlator, VV type correlator, right? If you just take the time integral here, you can find out. In any case, for more details, I suggest that you look up this reference, Brandenburg and Subramaniam. This is a review, very interesting review, and you please look up for more details if you're interested on the magnetic fields in turbulent medium. All right. Please note one thing, that the magnetic field is a pseudo vector. And think about what the pseudo vector and true vectors are. Right? In the mirror, the pseudo vectors do not basically transform just like a true vector. They have a different property. Okay, like a velocity will look. Try to think of a velocity in a mirror image, and try to think of a magnetic field or a current carrying wire in a mirror image. What is the transformation properties of these quantities? So it's a very interesting thing that the velocity is actually like a just the velocity is a true vector. Magnetic field is a pseudo vector. You can ask the questions in more topological sense. How do you generate a pseudo vector from a motion which is actually a true vector? How do you? So it is actually not possible unless you break certain symmetries. So this is one example of symmetry breaking. You break the symmetry in turbulence in order to produce something which is a pseudo vector. After all, you are trying to generate the magnetic field from the flow, or the velocity field, right? So this is one way to think. This is a simpler quantity, energy density. Basically, eta T turbulent diffusion depends on the energy density of turbulence. This tau C comes from the time integral. Okay, I showed you already here. You will write as a time integral of the right hand side. That's what is coming here. And under certain approximations, isotropy, homogeneity, and everything, you will get some sort of a correlation time type quantity, and velocity correlation times. But V dot V is like an energy, right? V square. And this is depending on the energy density of turbulence, and that leads to a decay of magnetic field lines, because curl of another curl has to be applied before you take the evolution. Del B by del T is curl of E. Curl of another E, and there is already curl sitting here. So that will give you eta plus eta T Laplacian B, which will lead to decay. Eta T is very large compared to microscopic eta in typical astrophysical scenarios. If you want to put up some number, look up these. This will give you certain numbers like the decay time from turbulent diffusion in a galaxy can be very short, like mega year, whereas the galactic lifetime is what, on the order of giga year or more. So how come the magnetic field has survived in the galaxies if the turbulent decay time is very short, like mega year, whereas the galaxy lifetimes are very large? So why do you still observe the magnetic fields? So that's a question. But the answer is also somewhat here, that if there is a term like alpha that can lead to the generation of magnetic field, which is true. And what is this alpha? Because you want to generate the pseudo vector, look at this. This is V dot curl of V. It's a very interesting quantity. It's called kinetic helicity. It's like a screw-like motion. If you were to imagine a motion which has a finite V dot curl of V, non-zero average, right? It's an on average non-zero V dot curl of V. How does the motion, you will picture it in space. So if you watch my cursor, it will look like a screw-like motion. It's like that. Normally in a 2D case, you see that if you take a curl of V, it will point in a plane perpendicular to V, and therefore V dot curl of V in very normal situations might be even 0. But here, curl of V has a component which is parallel to V. And this is a pseudo scalar. So it has a handedness. It's like a screw has a handedness, right? Left-handed screw and right-handed screw. So left-handed screw in a mirror will become a right-handed screw. And that is what you mean by saying the symmetry of the turbulence is broken. If it is not broken, the left-handedness must be preserved. But here, as soon as you have a kinetic helicity, it's a pseudo-scalar. In a mirror image, it will change its sign. Okay, that's what one means by pseudo-scalar. And you can work that out component by the component. Maybe I leave this as an exercise for yourself, that how do these quantities look in a mirror image. So suppose you have a quantity and you put a mirror along the z-axis and look at how the components of true vector and the pseudo vectors transform in a mirror image, in which case the mirror is placed along the z-axis, suppose. Okay. Just work out that, and then it's basically very fun to realize that how these quantities transform in the mirror image. Okay. So as soon as you have broken the symmetry of turbulence by having a finite kinetic helicity, it's a motion I'm saying is that it's like a kinetic screw-like helicity. It can have a right-handedness or a left-handedness, like that or like that. This quantity, alpha effect, you will keep hearing that alpha effect is dubbed as the main driver of magnetic field, large-scale magnetic field in variety of systems. In a variety of systems, right? Source of kinetic helicity, I will not describe much. Any system that is rotating and is stratified under gravity is expected to produce kinetic helicity on an average. Okay. On an average. Yeah. Remember that small v itself, the ensemble average is 0. It's just that the correlator, VV correlator, that need not vanish. And that is the origin of some quantity which is at a very large length scale. So please look up this more. I'm actually going very slow still. So let me come to my last slide. That there is a very important constraint on the evolution of magnetic field, and that is the magnetic helicity. So if you define the magnetic helicity as this volume average of A dot B, where A is a magnetic vector potential, which you might have learned is that curl of A is given by magnetic field. B can be written as curl of a vector potential. Why? Because the divergence of B is 0. Therefore, B can always be written in terms of curl of a vector potential, because divergence of a curl is always 0. So any quantity which is divergence free, you can write a corresponding vector potential for that, right? In general, for magnetic field, this is a magnetic vector potential. Okay. If you write down the evolution of this quantity helicity, dH by dt, you find that it has a form which looks like now the current helicity, but there is a multiplication factor eta. So it's a microscopically decaying quantity. Decays, but microscopically. That means eta is nearly 0 for high Rm, just like Re. Re we defined as Lv by nu, Rm is defined by Lv by eta. If eta is very small, Reynolds number becomes very large. Typically in astrophysics, the Reynolds number are very, very large, 10 to the 20, 10 to the 30, 10 to 40. These are the numbers you'll hear in astrophysics for the Reynolds numbers. Eta is nearly 0. That means this quantity is actually 0, going to be 0. dH by dt is nearly 0 for astrophysics. One could write here approximately equal to 0 for astrophysics. That means the helicity is a conserved quantity. Yeah? Helicity is actually giving you some sort of a topological link of magnetic fields. So it's a very interesting thing, and we have to meet in person, and I hope that day someday comes. Then only I can perhaps show you certain diagrams in which you can, but otherwise just read various papers and stuff. That even if you take two magnetic flux tubes, yeah, and you work out their helicity, flux is determined by what? Phi is basically B dot dA and stuff. So that's the magnetic field flux. If the magnetic field is like that, you can work out phi 1 and phi 2 by essentially taking the area element and going B times area element dA is actually the flux through this loop. So if these are interlocked loops, you can make whatever changes by motion to the magnetic field. You can cut them, you can do whatever various things, but still you will find that the helicity of the system is non-zero, remains the constant. It's a very tight constraint that the helicity cannot be produced or generated in a system. So if you started from say nearly zero magnetic helicity, it will remain nearly zero magnetic helicity. Very important prediction of therefore the alpha effect produced dynamo is that once you have generated a large scale magnetic field, you will find that at the large length scale there is always some magnetic helicity. But helicity is a signed quantity. So that definitely means that the field that you are producing in such a way must be bihelical. What does it mean? That there must be one sign of magnetic helicity at large length scale and the opposite sign of magnetic helicity at the small length scales or the scales of say motion, such that the net magnetic helicity remains zero. So in that sense, it's an effective tracer of the origin of magnetic field. It's a scalar quantity, so roughly we can say that it's a simpler quantity than the vector magnetic field. So a lot of people are very interested in the properties of magnetic helicity and determining those magnetic helicities in various systems, because observing their properties such as, for example, they're bihelical or not, will tell you what is the origin of the magnetic field. In this case could be the alpha effect. So we'll keep hearing about the alpha effect as the main driver of the magnetic field in the universe, or in various objects in the universe, and various systems there basically apply this. Please look up these papers. Even if this is very, very tiny and non-zero, even then this is shown, for example, in this paper, 2050. It's a very active area of research even now. So people are continuously working on these ideas and concepts. That even when you have a magnetic reconnection event, that in which the magnetic field lines are connecting and changing their so-called topology, even then you find that the helicity is typically conserved. And one draws a difference between magnetic helicity, which is A dot B, and current helicity, which is J dot B. This is not conserved. This is conserved. Okay. So it's a topological invariant. That you can do various changes to the fields, yet this remains an invariant of the problem. And finding various invariants is always a good goal in physics. So I think I'll stop here. I think I've covered fluids, plasma, and also given you a little flavor of how do you think about attempting the question of large-scale magnetic fields. How do you produce those large-scale magnetic fields? These are very active areas of research. People are continuously working. It's a very isotropic and very simplified equation written here, but in more complicated situation, many number of terms appear, and these are also tensorial objects. And what are the effects of those in detail in a specific system? It remains to be understood. One doesn't really know fully, but it gives you a hint of how from very small scale motion you can drive a very large scale magnetic field. How does that happen? At least this flavor is given. And that leads us to some understanding of these origin of these large scale magnetic fields that are observed, routinely observed. Okay. So please look up this reference, and there are many references quoted in that, and for more knowledge on the magnetic fields. So it's a fascinating topic, and I hope you have understood something from this. So please raise your hands in case you want to ask questions, and I will then try to unmute, and then we can at least take a few questions. I think it's still a few minutes, so maybe another 10 minutes. I will only be responding to your questions if you have some. So there are some questions like, so please raise hand. You know how to raise hand. You go to the participants and there will be something option in the 3 dots you see, and then there will be option to raise hand if you want to raise hand. I already can answer something. Shawan asked, please explain a bit about magnetic field generated due to conversion of kinetic, or you can also just send a chat, that's also fine. A bit about magnetic field generated due to conversion of magnetic. So I just explained it, right? How do you convert the kinetic energy into the magnetic energy? Right? So that's the converger term was the sulfur effect. That is exactly how you convert it. Right? Any motion will give you some sort of a magnetic field. After all, these are motion in plasmas. Moving charges giving you magnetic field is not such a surprise. And the question was, how does it survive at such large length scales? And that's one glimpse of that. If your turbulence has this kind of symmetry breaking, you will be able to see that from here. What is the double average? Well, double average is essentially you can take multiple averages, right? You can there is no as such any limit on that. I take a quantity, I take its average once, I take it average again. In the Reynolds rule, you will find that this is always, it doesn't matter how many times I take the average of the quantity, every time the ensemble average will produce you the same mean. Okay? But it's not necessarily the case when you are taking a filter. So think of a random variable and apply some sort of a smoothing kernel or smoothing filter. You apply it once, you'll find one answer. You'll apply it twice, the same filter. You'll find that your answer, the so-called smooth field, has actually changed. Just think of Gaussian filters when you are dealing with some random variable and data. So anyone wants to ask question, please raise hand. I will still wait here for another maybe 5 to 10 minutes. 5 minutes maybe more. And or just send a chat in case you still want to ask something. Yeah. So please feel free to ask anything. You may have some questions, and I have uploaded all these things to PBWork, so hopefully you will find this. And in the afternoon, you will hear something from the Dhruba about the turbulence. I hope I have covered enough basics. How do you filter the quantities into mean and fluctuations, and how do you think about transfer and inverse transfer? So after all, this is exactly an example of an inverse transfer. The energy in the small scale has been transferred to energy in the large length scale, right? So it's like an inverse transfer. In turbulence, you'll hear about the direct transfer, which is the large scale eddies will be actually cascading down to the smaller and smaller length scales, and that will give you some sort of inertial spectrum. So that you'll hear from Dhruba in the turbulence lecture. But I think very basics and what the equations involved are actually covered. So hopefully you'll have no difficulty in following those lectures. So anyone, please feel free, don't worry. If you can hear me, please just raise hand, ask directly question. That also at least adds to some fun. Otherwise, it's very boring to just speak to the computer. Yeah. So don't worry, even if whatever the question is, just try at least one person, try something. Nobody's asking yet. So I'm just still waiting. If something was not clear or something was very rushed, you can ask me to repeat, or I'll be happy. Otherwise, this is my last lecture, and wish you very good luck with your other courses and further learning. So anyone? Everybody is so shy. What was kinetic helicity of alpha? Kinetic helicity of alpha. No, alpha is the kinetic helicity. Alpha is the net kinetic helicity. Ayush asked to unmute. Okay.
Hello, sir. Am I audible?
Yes, Ayush. Go ahead.
Sir, when we are talking about the plasma physics in the
Yes.
astrophysical scale, then we are talking about the ions over here, like plasma consists of ions, positive and negative ions, right? So
Yes.
in in total, when we are talking about in the cosmological scale, then isn't it like they are balancing each other and they're the neutral?
Well, when you are talking about what, it's a little bit broken voice. So can you repeat?
Hello?
Yeah, yeah.
Yeah, I was saying like when we are talking about the plasma and the cosmological scale, then
Yes,
the ions to the opposite charges, they should balance each other and become the neutral. And
that's right. Yes, yes, yes.
so why isn't it happening? Because when we are talking about the plasma and the ionosphere at our upper surface, then
Mm,
it is like a charged particle
mm,
with a huge amount of kinetic energy. And
yes.
even in the cosmological dust as well, it contains a large amount of energy
Mm,
with the charged ion. So why
mm.
isn't it neutral and consists of the negative that it drives it away?
Why is it? Okay, so I'm just trying to guess what you're trying to ask. Is that there is enough, there is ions and electrons. There is no net charge as such in the universe, right? So they are always in balance. Everything has started, suppose, from largely the hydrogen atom. If you go to very early universe, so yes, there are as many positive charges as there are negative charges. For defining the plasma, we have anyway taken a plasma element which is charge neutral always. Right? What I was trying to say, I think, in this earlier thing, is that even if you create some sort of a charge imbalance, you can create charge imbalance by certain mechanisms, say, such that the plus and minus, although they are equal in number, they are separated by some distance, and therefore there will be a local electric field in the rest frame of the plasma. Okay.
And there is one more thing. As we were talking about the viscosity in the plasma matter
Yeah.
in the cosmological depth, and viscosity, as we have understood, is resistance in the flow of particles. So,
Yes.
what is that resistance in that in the plasma in the cosmological scale?
What is that? What? Sorry. What is that?
What is that resistance that is opposing the flow of the plasma? And
It's very, very tiny. See, it's very. You mean you are asking about the magnitude? If it is very large, or what?
I'm not talking about the magnitude. I'm talking about that thing, that nature of that resistance. What is that resistance that is opposing the flow of?
So it's just like collision, right? It's just like friction between two species, which is causing decay of the momentum.
So it is
Viscosity.
like internal collision.
It's
Internal.
just like an internal friction. Yes, it's an internal friction. It is always accompanied by a shear stress. So you can imagine the two moving plates, and if you draw a lateral surface, suppose I go back to some picture like that. Yeah, you can think of a layer which is separated by this thin line here. The momentum of particles here has a larger momentum than the particles here. So there will be a flow of particles from one layer to another, and therefore changing the overall momentum of one layer against the another layer, because this layer here below is actually trying to drag these particles below, drag it to reduce their momentum. And in that sense, you can think of any layer microscopically. You just try to think layer by layer, and it's a friction between two parallel layers that is causing the momentum loss through the viscosity, which is actually can be written in terms of the transverse gradient of the
Okay.
velocity, right? Transverse gradient. That's what I said, that it's a shear stress. It's a shear stress. It's a proportionality constant. So it's like just like the two plates that are moving against each other, causing friction. So that is how you think about the viscosity. Whichever species in the plasma is dominant species for causing the momentum transport, that will dominate your calculation of viscosity.
Okay.
So sometimes, for example, electrons can be the main driver of the current, because the ions are more heavy and they are not necessarily moving so much. Quasi-neutrality of the charge is maintained all throughout, but you can imagine that frozen plus ions here, which we are not supposed allowed to move, and electron soup is basically just moving in one direction. If you take any cross section at any given time, the charge in that particular volume is always zero, but it's only the electrons that are moving. So you could think that the resistance or the microscopic resistance is coming mainly by the electron and ion collision, yeah, because they are of course colliding with each other, and the current is driven mainly by the electrons, whereas these fat ions, they are the main drivers of momentum. So for viscosity, you may want to consider the ions, and for resistance, you may want to consider the electrons. So you can think of it like that. Whichever is causing most transport is the, yeah, in that sense you can think. So there is one question by Arpita. Can we use magnetic helicity to understand the kinematics of spiral arms of the Milky Way galaxy? And if so, then can we use the concept to understand spiral arms of other galaxies? And what is mechanism of the ring galaxies? Yeah. Okay, so see, the origin of these spiral arms is very different that we at least now have come to know. That is a topic of something called density wave theory of the spiral arms, for which you do not even have to invoke any magnetic field. Remember, the magnetic field, spiral arms are produced even before, and spiral arms are produced even in systems when there is no magnetic field or very weak magnetic field. So the magnetic helicity and the magnetic quantities have very little effect on the flow as such. So it's still by and large kinematic, as I was saying. So the origin of spiral arms, in most cases, you can very safely perhaps say today that that is not due to the magnetic field. There is also a magnetic arm, by the way, and they are phase shifted for each galaxy. Origin of those magnetic arms is a very interesting topic, not very well understood yet. But origin of these is usually spiral arms of the galaxy that we know in terms of the density wave theory. It's a topic of galactic dynamics, and so I would say that the magnetic field is not playing role for that spiral arm in the galaxy. That's also not the magnetic helicity. Yes. Spiral arm is, of course, inducing some sort of anisotropy in the, or non-axisymmetry in the galaxy, because otherwise the galaxy would have been axisymmetric. It's a non-axisymmetric thing. So it adds more complication to the problem, to the system. But as such, the origin of these beautiful spiral arm, that one can think in terms of density waves. It's a very interesting topic in itself, without any magnetic. There is a question by Manish. Why is the magnitude of magnetic field is shorter in the perpendicular direction of major axis, north of the galaxy? Correct. Yeah, it's a good question, Manish. What happens is that in most systems, there is a mean flow as well. The thing I was trying to ignore, there is a mean flow, which leads to the further boost of magnetic field in the direction of the mean flow. What is that mean flow in galaxy? So we know that the galaxy is in differential rotation, right? It's a very typical Keplerian type differential rotation. You know Keplerian differential rotation, right? Omega goes as 1 over square root of r cube and stuff, right? Different rotation, when you write your mr omega square and balance it with gravity, you find that you have a Keplerian profile in which the rotation angular velocity has a radial dependence. That's a definition of shear. So these systems are actually shearing systems. So if I take a small element of galaxy, say here, small element of galaxy, you can approximate the flow in that galaxy as a shearing motion, which is small arrow here, larger and larger arrow as you go to a larger distance. So it's a shearing motion, which is in a phi direction, Okay. So there is a stronger motion in the phi direction, and therefore there is a more systematic magnetic field in the phi direction. That is the origin of this larger arrow in the phi direction. There is, of course, it's not always the phi direction. There is a finite pitch angle. It's a very nice and interesting problem. What is the pitch angle in a variety of galaxies? It turns out Pitch angle you define as the angle of opening. If I draw a circle here, suppose I draw a circle at this radius r, and if I draw a magnetic field vector at this point here, the angle that it makes with a tangent or with the circumference, the angle that it makes, that is called the pitch angle, which is essentially, you can imagine, it's a quantity which is br by b phi, b radial by b phi direction. B phi is always larger. Also in the sun it is the case. B phi is typically larger because the toroidal motion or the velocity field, as you see that it is coming from the stretching, right? It's coming from directly the stretching. We have seen that the magnetic field will be frozen to the plasma. Where is that? Yeah. When the magnetic field is frozen to the plasma, if there is a one direction in which the velocity is largest, magnetic flux or field will be frozen and will be stretched maximally in that direction of stretching. In most of these systems, like galaxy and the sun, there is a differential rotation, which is a phi-like motion, and therefore the magnetic fields are typically larger in the phi direction. But there is always this BR component. It's a very interesting thing that without BR, will your B5 survive? So that is a question with all this anti-dynamo theorem and all. I suggest that you read more. But suppose you have no way to produce a little bit BR, that small little BR is actually supporting that large B5. It's a very interesting thing. Because otherwise what will happen is that I have a field which is, say, poloidal, which is pointing in north direction, say, and I put a velocity field which is phi in this phi direction, so that is a toroidal magnetic field. In time, I will stretch all of this poloidal field into this toroidal field, but then I have no more field left to stretch further. So what will happen to that solution? In that solution, all of that B phi that you have produced, it will actually just be decayed by your ohmic diffusion, and ultimately you lose all the field. So it's very, very important. By stretching, you have produced one component. Stretching by flow. So I'm just trying to draw this arrow. These are the things that one could do on the board if you met in person. But sorry that this didn't happen. This damn corona. But anyway, so if you have this so northward magnetic field, and you have a y or phi direction velocity field, you stretch to make the field from B, call it BR, to B phi. But once you have stretched all of BR, there is no more BR left. So what will happen? There is nothing left to stretch. So please read about something called Anti-Dynamo Theorem, that what are the flow properties that can sustain the magnetic field. So you'll find that just purely 2D velocity fields cannot sustain a magnetic field. It has to decay. So it's a fully 3D problem actually in some sense. So the game is all about, not about the how do you generate from the north to this phi field through the stretching and the differential rotation. Of course, that component will be large as you see in this galaxy. The game is how do you regenerate this poloidal field from this B phi to BR? How do you regenerate? And that is what is done by the alpha effect. So if you look carefully, alpha is the parallel component. EMF is parallel to the B. It's very interesting. Okay. So when you take another curl, you'll find that you'll get a contribution through the alpha effect to produce back this poloidal field. The dynamo is not about stretching. Dynamo is all about producing back the field which you were stretching before. Okay. So this alpha is the source of that poloidal field, so-called poloidal field, which is in this case drawing was the northward field. Ayush has asked another question here. But that was a very nice question, Manish, that why is that so? So I think I have answered that, and think about the pitch angle, and it cannot be zero as such, because then it's a disaster, but it is typically very tiny. So it's a very tight wound spiral. In fact, that's also a very interesting thing, that the magnetic spiral arm is not perhaps as tightly wound as the fluid or gas spiral arm is more flared up. The magnetic spiral arm is more tightly wound. When we are talking about aurora generating at Earth's north and south pole, then due to the flow of plasma from sun, it drives it where and disrupt the magnetic lines of the Earth, since north pole is like magnetic lines. So why does aurora generate at north pole? What does it mean? Since north pole is like emitting lines and south is the one absorbing it, so why does aurora generate? No, it's not about that. For that, you have to just watch certain movies. I to see how does actually that happens, but let me try to see still if the diagram is enough. Where is that? You say the references for Anti-Dynamo Theorem. Yeah, there are many actually. You can just look up Cowling's Anti-Dynamo Theorem. And there are some lecture notes that are publicly available, I think. There are lecture notes by Chris Jones, in which there are various anti-dynamo theorems listed. Look up this book by Moffat on magnetic field generation due to electrically conducting plasma, the book by Moffat, or any standard text on the magnetic fields and dynamos will give you all about that. It basically starts with anti-dynamo theorem. But otherwise, just look for Cowling anti-dynamo theorem. It should be enough for the moment. I'm just trying to get a picture of Earth. I hope I have it. Yes, here. But this is not a very useful picture. Yeah, maybe here. So suppose there is a solar plasma that is coming here. Those particles, it depends on the level of magnetic field that are coming with that plasma, but typical strengths are very weak. So those charged particles are actually trapped in these magnetic field lines. Right? Just think of them as trapped field lines, and they'll just spiral along the field lines. They are not breaking these field lines all the time. Most observers, they are not breaking the field lines. They are simply trapped in these magnetic field lines. If all the magnetic field lines are continuously broken and reconnection is very, very severe, we can have very severe magnetic storm. In fact, there are numbers that you can work out that what type of magnetic field with what morphology can wipe out the life from the planet. It's actually entirely possible, by the way. Okay. For reconnection, typically, you need an incoming plasma should have a magnetic field which is going opposite to that. That's what facilitates a much faster and much efficient reconnection. If that kind of situation with a very strong magnetic field coming in happens, a lot of these field lines will be disturbed. In fact, that does happen to some extent. Where is that picture? Yes, here. That's why your say the magnetopause here and here. The sun side of the Earth, the magnetic field lines are pushed by these impinging particles, but still it is not very weak field. Once you invoke your stretch argument of the flux freezing. Once you have pushed the magnetic field, it has been packed to a smaller, tinier space. Thus, the local strength of the magnetic field of Earth has actually increased a lot, whereas this particle is expanding, in a sense, and continuously weakening its magnetic field, whereas the Earth's magnetic field here has become larger. So, at some point, there will be a magnetopause, hopefully always for the rest of our lives and future generations. This doesn't come very close to the surface of the Earth because that is going to be totally devastating. But then these charged particles at some point are basically trapped in these magnetic field lines, and now they are traveling towards the poles. Right? These charged particles will just spiral towards the poles, and that's where you get this aurora like this. Because now these charged particles are simply hitting. It's just like I have a molecule, and some charged particle came and hit that molecule, excited it to some level, say 3. From 3 to 1, it will come back, and then will lead to some sort of a radiation. That radiation is what you see here. So there is no problem. It's not only at North Pole, even South Pole has aurora. Because it's going both ways. Depends on the charge of the charged particle. Which particle goes here and which particle goes here depends on the charge of the charged particle, right? Plus and minus will go opposite directions. So no problem. And these field lines are actually protecting us in that sense from these solar particles. Yeah. So I think if you have more questions, feel free. I can continue. Otherwise, it's also fine. There is another question by Pralay. Is there any significance of the Faraday time scale in reality? Yes, there is a great significance. Of course, that number is calculated. One should know these numbers, first of all. That what is the typical time scale over which your charge imbalances are sorted out. But these charge imbalances may not be sorted out. Suppose you go to very early universe, very, very early universe, when the time scales are anyway very, very tiny. Yeah, these may become relevant. The temperature is also changing. So you have to take into account the temperature when you determine the Faraday time scale. Suppose this number is in some regime. Just that in astrophysics, we are not very much interested in these time scales, right? But in suppose in lab, when you are all the time trying to make a plasma, right? We are trying to come up with more sustainable form of energy and not relying on the say the fossil fuel like the diesel, petrol, electricity coming from those, coal burning. So the future is, at least in principle, one should be thinking about sustainable form of energy, and one form is actually this plasma generation that requires plasma generation. Read up about the stellarators, where the ultimate goal is to come up with a clean energy source in which you are generating plasmas, and you are very typically in a laboratory plasma interested in these kind of time scales. It's very, very significant. Yeah. So one has to then worry about various kinds of instabilities that will develop within these time scales, and that can even actually cause havoc in your, and one has to overcome certain challenges that come in your making plasma in lab. So look up these nuclear fusion based energy source and yeah, stellarators and stuff like that. So yeah, one should know at what time scales you should start to get worried. What is the temperature? So what was the temperature dependence here? T to the minus. So these numbers at higher and higher temperatures, yeah, these numbers will go down, right? It will go further down. But at the lower temperatures, in lab, suppose you go to very low temperatures, these numbers can actually go up. They may come within your reach. But it's good to know that for most systems that we are interested in, the galaxies and stuff, they are very tiny. But once you have no magnetic field, suppose you can ask the question in a very different way, that I start with a system which has no magnetic field. Now this equation is of no use, right? You will actually go back to rely on these time scales to give you something to begin with. Because over those time scales, there will be some very tiny fluctuations, some departures from the usual barotropicity. I didn't spend too much time on barotropicity of the fluid and stuff, but in desperate times, you will rely on these time scales. Let me put it that way. Yeah. Please suggest a good book on the subject. So actually, yes, I think one thing could be this review. For fluid part, you can look up various textbooks. Of course, I have suggested or listed some here. Right? I think I've suggested some here, like this for fluid part here, Ekeson. For the most on the dynamo things, I think I gave this reference Brandenburg and Subi modern text because the concepts are very classic and very well described in that textbook. But then there are various reviews. You can actually look up various reviews on dynamo. One I have listed there, but there are reviews by Anwar Shukurov and stuff. So you will find those listed in that reference, Brandenburg and Subi. Various numbers, if you are interested, you will find in this reference also, Brandenburg and Subi. So given this is my last class, I am just trying to address as many questions as possible that you may have. And so yeah, I think I'll wait maybe a couple more minutes in case you have something. Otherwise, very, very good luck. And yeah, study well these things. Okay, so I see no more chat and no more hands raised. If you still want, maybe I'll wait one more minute and then we can close. Okay, so I think it looks like all is good. Please check the PB Works website where this updated slides are all there in PDF form. So I hope that is useful and make use of it, and wish you all the best. Thank you. There is a question now that if I have some question, can ask Google Forms. Google Forms I may not be checking. So if you do have a question, just send an email. I think that works the best. Google Form I may not be checking at all actually. So just send a mail. Okay, thanks.